before I give you the note, what you say, right? So we're gonna take a look now at Hooke's law, right? And we should remember this. Hooke's law tells that what? F is proportional to extension, right? Provided that the elastic limit not exceeded, right? What would happen if you exceed the elastic limit? Right, here's the little curve here. And if you exceed the elastic limit, would it start back at the origin? No, right? It will start back at some point later on. Because it underwent what? What is called that? It's no longer elastic, so it's inelastic, right? So it's called plastic deformation, right? And then the graph looks like that. What do you think happens here? What do you think will happen here? No more force, it will break. All right? So your graph looks something like this. All right? Don't draw it, I'll draw it. We need to figure that's now and label it, right? But so we know this. From Hooke's law, we know this, right? So that's your form 5 stuff. Today we're gonna take a look at something called stress and strain. Right? Stress is what? Stress is whenever you have force acting per unit area. So stress is technically what? Pressure. Very good. Pressure. And strain represents is a ratio of how much extension you have to the original length. That's okay? So strain represents the ratio of the extension to the original length. All right? So these are two new things. And then if we combine these two, if we combine stress and strain, we're going to get a new quantity called Young's modulus. Right? So our focus today is on these things here. That's okay? All right, before you write that, take these small notes, right? As I said, the handout I did for you, you'll have this. So you gotta write this, right? So forces applied to a material. Take a small note down, right? Forces applied to a material may cause it to become deformed. May cause it to become deformed. May cause it to become deformed. The material is said to be stressed. The material is said to be stressed. The material is said to be stressed, and as a result, it is said to become strained. Note that stress is defined as the force acting per unit area. Force acting per unit area. And strain is the ratio of extension and its original length. tensile stress. This one. Tensile stress results in an increase in the length of the material. In the length of the material. Increase in length, right? And compressive stress. The next one. And compressive stress results in a decrease in the length of the material. Results in a decrease in the length of the material. Right, under that, note that the ratio of stress to strain. Note that the ratio of stress to strain is called Young's modulus. The ratio of stress to strain is called Young's modulus. It's called Young's modulus. Right, just make a quick note next to them. Yes, SI unit here, pascals. No SI unit here. SI unit here, pascals. Yes, next one. Okay. This one. Where's my okay, yes. Consider the following. Show it first. Right? Draw this one. Right? It's a stress versus strain graph. O to A to B to C to P, right? Use the same label then, right? Right, the only straight line is from O to A. All right, so I want to make sure you understand the difference between two little things here, right? So what you see here to here is where Hooke's law is applied, right? So questions will ask you questions will ask what is the proportional limit? The proportional limit is up until here. Proportionality, that's this symbol here, does not happen after this. Right? If they ask for your elastic limit is here. Right? Because if you were to go beyond here, that's the only time that it doesn't go back to the original. It goes back to a new strain point. Right? So up until here, the object behaves, the object undergoes elastic deformation. Right? But once you exceed here, all of this is plastic deformation. That's okay? Here's the max stress and here's where it will break after that. Everybody okay with that? So the most important thing you need to remember here is what is the elastic limit, right? And what is the proportional limit, right? That's okay? All right, good. Take this small note down. From O to A, from O to A straight line through the origin. From O to A is a straight line through the origin. Stress is proportional to strain. That is, force is proportional to extension. All right, here for you. Force proportional to strain. Sorry, strain proportional to stress and force proportional to extension. Right? So so since force proportional to extension, Hooke's law is obeyed. All right? That's it. Constant. A and L. Since. Sorry. Since. Yep. Hooke's law is obeyed. Hooke's law is obeyed. All right, ready? Next part. A is the limit of proportionality. A, please make sure you label it just like mine. Though. A is the limit of proportionality. A is the limit of proportionality beyond which Hooke's law is not obeyed. A is the limit of proportionality. That's right here. Once you go beyond A, Hooke's law is not obeyed. Right? A is the limit of proportionality beyond which Hooke's law is not obeyed. All right? A to P is the elastic limit. So sometimes you can put L here if you want. A to B or L, A to B or L is our elastic limit. Is our elastic limit, full stop. If the elastic limit is exceeded, if the elastic limit is exceeded, if the elastic limit is exceeded, then the material will not regain, then the material will not regain its original shape and size when the force is removed. then the material will not regain its original shape and size when the force is removed. Oh, that's a tree alone. Well, I mean, sorry, like cover module 3. To make sure we cover module 2 after. So you can trade this out, this will cover most of module. Right, note that O to L, sorry, note that O to B, note that O to B, note that O to B, the object undergoes elastic deformation. Note that O to P, the object undergoes elastic deformation. Right? After P, next line, after B, it undergoes plastic deformation. Right? After B, so that's all of this here. That is what we call plastic deformation. Right? Put in bracket, the strain is permanent. The strain is permanent. Right? C is the maximum stress. C is the maximum stress. And D, the wire breaks. And D, the wire. Alright, that should be good. Right, so I gave you all of it, right? Alright, so what are the ingredients I give you earlier? Let's go back to the graph, right? Let's look at the first case. If I give you a graph that looks like this, and it's a stress strain graph, what does the gradient of this graph give you? What's the gradient? Stress strain. Young's modulus. Right? So the gradient here is stress over strain, right? So if you do a graph like this, the gradient will be Young's modulus. Right? If you could just say pressure, not in this case. Right? In a similar unit, but not the same thing. Right? So the gradient is Young's modulus. But if I give you a graph like this, and Nathan, if I give you a graph like this, what does the gradient give you? No, it's force versus extension. What does the gradient give you? Okay, right. So that's one. They can give you the spring constant. But is there any way to find Young's modulus from this graph? No, we're not sure. All right, so let's see. Did I give you the symbol for these things? I think I gave you the symbol, huh? That's up there, right? Right. So remember, we know what stress is, right? We know that stress is force over area. We know that strain is extension over length. What's Young's modulus again? So it's force over area divided by extension over. I'm using x for extension, right? What will the formula simplify to? What would this simplify to? The L will flip up, x will go there, FL over AX. Right? So how can this graph help you find Young's modulus? Isha, oh, that'll help. How could a graph of force versus extension help you find Young's modulus? And I just wrote here for you that Young's modulus is equal to F by the length over the cross-sectional area by X. How you can use a graph like this to help you find Young's modulus. And Mikhail, any ideas? What if you're showing an idea? You're showing here. Ishak, any ideas? None? So what does gradient normally give you? Gradient is normally what? What on the y divided by whatever on the x. So it's f1x, right? See that here? So can I do something like this? Can I leave f1x here and move across the A and move across the L? Yeah. So can I say that the gradient is equal to cross-sectional area by Young's modulus all over, like that is your gradient. Right, so if you get good graphs, you have to be able from the graph to find Young's modulus. Right, you will see a lot of these on graphs, but we're not going to show on graph. Right? So the reason I gave you these, right? You have to pay attention to the graph that you're drawing, right? I'm supposed to make you draw a graph now. Anybody have graph paper? Nobody have? All right. Let's see if we can find one without advantage. No, no, it's a basic guy now. No, equal, yeah. Yeah. Okay. Right. So just pay attention to what units you have on the axis. Let's copy it down. Right. So in short, Young's modulus from a stress strain graph, gradient. Young's modulus from a force extension graph is gradient by the length over area. All right. You might find what's moving this morning. Huh? Anybody here on read this stuff? Read the height, right? We'll just all right, let me see if height, but still good. Right, right. Yes, all right. It's not the best, but let me see if we can use it. It's on full screen. It does. All right. So this is the best I can do here. Here what I'll do, right? I'll leave the graph up and I'll ask questions, right? So example one. Look at the graph there. What type of graph we have? What type of graph we have here? Force versus extension. Nice. Pay attention to the unit. Force is in newtons, extension is in millimeters, right? So any value you read off with one is in millimeters, right? All right, ready? Part one. At what load, Adam, you do this first one. At what load did the wire begin to deviate from Hooke's law? Right. Yes, around 60. So you start a curve somewhere here, right? Yeah, really. Right. So we all had to go with like 55, around 55 newtons. Okay. So I'll quick list capture the graph in the book now, so you have something to look back up. It will be perfect. Just a quick list text, so you have something to look back up. So yes, we can see about 55 newtons, right? Nathan, next part is yours. That's now ask. Oh, wait, yeah, yes. Right, so just a little sketch. So this point right here, we'll average at about 55. Right, so the first part is at what load did the wire begin to deviate? We can say around 55 newtons. Right? As soon as it's no longer straight and it begins to deviate, that final point there will be a value you're looking at. As we said, we'll average it to be around 55 newtons. All right. Next part, Nathan. What was the stress in the wire when it began to deviate? What was the sorry? What was the stress in the wire when it began to deviate? So look back at how to find stress. Huh? F over A, right? And F is how much? 55 newtons, and if you have to average, A is what? What are you looking like? 7 points. All right, yeah, you look in the middle. It's all right, yeah, you go with that. We'll go that, please. 10. So stress is force over area, right? The force is 55 and area, sorry. Wait. Something wrong. I think I have value. 72. Mikhail? It's force and area, right? We read off the what? the extension. How we gain area? I'm not sure if you're seeing it, right? But look at the top here. You have the length of the wire and diameter. So you find area. Psi r squared. Okay. The value that we found here, that value is the extension. Question asks us for stress, right? And as Nathan said, stress is force over area. So use this value here and find the area. Right? What's the area again? Pi r squared. But that's right. Please remember that's 1 millimeter. So you have to divide by 2 and work in meters. Okay. Yeah, you can go to meter and then fine. Right. How much are they got? One line you could look at the look at the code, right? I want to write it there now because I can't use this screen. I was thinking giving some trouble. Right, so as you all said there, we're trying to find stress. Stress is force on area. The force is 55 newtons, and the area is 1 by 10 to the minus pi by 1 by 10 to the minus 3 on 2 squared. Right? Yeah, to find half of the diameter, right? How much is this? Tell me the final thing now. 7 point what? 7.85 minus Now it will be minus. Yeah, the final thing. Yeah, I think I know who right now, but I think somebody came already. Okay, all right. Right, how much you got? Right, yeah, 7 is normally be a large value. 7 by 10 is 7. That's what I got. 7.0 and then or 0. Right, so that is your stress. Everybody okay with this? Right? Yeah, can't see. Pay attention to your units and when you're putting the calculator, right? And all you're doing math something as well, right? So you should have an idea of what to expect. Right? This is minus underneath. So when it goes on top, it becomes positive. So you should get a positive value here, right? Next part. Next part, they would like you to find the strain that the wire undergoes at that point. Hold on, eh? Find the strain now. Remember, it's a ratio, so it's okay if you're in millimeters, right? But both must be the same thing. If one in meters, yeah, the first one in meters. First one in meters, and the second has to be in millimeters. Find your strain now. Find your strain. Take your extension and divide it by the length. Right? They gave you the original length. Right? And remember, what did we use for the extension? We use 0.75 millimeters. So convert to meters one time. And the original length is 2. Right? So would you get minus here at the indice or positive? You'll get minus, right? How much you get? 3.75 by any unit? No, because it's a ratio, right? And the last part, they have to Young's model. How you doing now? Stress over strain, right? Right, but I need a favor. I need you to find Young's modulus 2 ways. Right? You can go ahead and use stress on strain, but I also want you to use it using this method here too. Right? Use both methods and find it. Right? You might have to take your time and find a gradient, right? You can use 0, 0, and you could use the value that we had there, 55, 0.75. So find Young's modulus 2 ways, using the formula stress on strain and using the one that we derived earlier. Right? You will see this question a lot in exam, right? past papers, you will see a lot where you have to sketch a graph, find young point. Right, finding out for the school based level, yeah? School method. Wait, one hour, right? Right, so as I was saying, to want to read off 2 points, right? Use here 0, 0, and use this one here. We use 0.75. Remember that's millimeters, huh? 0.75 millimeters and 55 newtons. Use both methods and tell me what you get. Right, the first method should be is the one that we have here. That's stress over strain. So that would have been 7 by 10 to the 7 divided by 3.75. Right, you'll always recognize that a Young's modulus extremely large, like 10 to the 10, 10 to the 11, and 10. How much you all got using the first method? How much? 1.867. 1.867 by? Try the next method now and see if you get close to that. Pay attention to your side units, right? That 2.75. That's our unit, right? We'll be getting it. Okay, like the same thing, right? So what do we have for gradient? Gradient is equal to y2 55 minus 0 over 0.75 by 10 to the minus 3 minus 0. Right? That'll give you gradient. How much is that? 55 over 0.75 by 10 to the minus 3. 73.33. Okay. Seven. Yes, divide 55 by 0.5 by 10 to the minus 7.333. Okay. Right? So that is your gradient. So all we need now to find Young's modulus, we multiply the gradient by the original length all over the area. So that will be 7333, one more 3, multiplied by the length, which is 2, all over the area, which is pi by r squared. Right? I'm not sure if we kept that value, but that'll be 1 by 10 to the minus 3 all over 2 squared. Right? So you have to work out the area. And you should get the same thing, huh? You should get back 1.87 by 10 to the 11 Pascal. You're supposed to get back the same thing. Everybody okay with that? So we could use either method to find Young's modulus, right? Let's try our next one. Any questions online? Same question I could 3 times. Next one, right. First one was 2003, 2004. I can only work down, I didn't show you that just yet, right? Let's try this there. So what stress would be required to increase the length by 0.15? And they gave you the Young's modulus for this time, right? A way to be aware and how many values, huh? Young's modulus is generally around 10 to the 11 and 10 and 12 and 10. Okay. right? Go ahead, try that. Right, and what they give you? They give you Young's modulus, and they give you 0.15%, right? And then what you find stress. Try that in. You have Young's modulus, you want to find stress, the more than like you want to need. Yeah, if you got how to get right? Right, so we have Young's modulus. How do we get stress? They give us no other values. So how do we get stress? Everything has to be, yeah. Right. Right. What the strain? The strain would be that is the increase. Like everybody all right, it goes in, go ahead. Please remember 0.15% is not so. It's how much? What is 0.15%? 50 of 100 notes, that's 15%. 0.15 over 100, right? Okay? Alright, try it out. I'm gonna do this now. Right, so again, what again the habits of this, right? They want us to find stress. So we know that stress is force on area, that's not gonna work. Right? We also know that from this formula here, we know that stress is Young's modulus multiplied by strain. Right? We already have Young's modulus. What we had to do now is see how this is going to help us find strain. Right? Remember, strain is what? Strain is the extension divided by the original length. Give me 2 minutes, try something. All right, so let me see what it come up with now. So let me start this screen. I'm gonna go way down. So all right, so let's keep the original length as L. Right? Keep the original length as L. We don't know where it is, right? So let's pretend, all right. Let's pretend it's some value L. What will the extension be? How much? X by. So they said to increase the length of the metal wire by 0.15%. So the extension is how much? Huh? By L, right? Yeah. So therefore the extension is that percentage by L. Right? Because now the original length is what? So it's like this. You have your original length and then you want it to increase by 0.15%. So you have to find this is the extension here. Right? This is the extension. So in order to find the extension, it will be 0.15% of the original length. What will happen to the lengths? They'll cancel off. So you'll end up with your strain being 0.0015. That's what your strain will be. Right, one? Yeah, that's not there. Right, we'll call this specimen out. So your stress will be 1.2 by 10 to the 11 multiplied by 0.0015. That will be your stress. Double kind Sure. Next part easy. What's that again? 1.85? Second power? 7. Nice. Next one. Cross-sectional area is that. So they gave you the cross-sectional area in millimeters squared, right? We don't really want that, eh? Convert in meters squared. How you do that? How you convert millimeter squared to meter squared? How you convert millimeters to meters? Divide by 1,000. So how you will convert 2 sets of millimeter? Divide by 1,000 twice, right? Yeah, so divide by 1,000,000. Right? Divide by 1,000 squared. Okay? So think about it like converting millimeters twice. Right, find tension. Tension is what? Joseph, tension is what? Oh wait, no. Connor, tension is what? What's tension? Which are these quantities here? Check and see. Which are these? Right, tension is that. So find where, find. Huh? 10 to the 8. On the shop, 0.0015. Right, what formula we using here, Connor? What formula we using to find that? Right, nice. Force is equal to stress by C1. Across the area. Stress by area. Force is stress by area. Work it out quick, tell me what you got, huh?
Get around TNT. What are you taking on?
Right, remember T divide 2 by 1,000 squared, right? I am getting what, 3/6 by 10 to the 2, 360? 360 newtons. Got it? Good job?
Yeah.
Any questions online? Okay with that, right? Question again, sure. Right, pay attention to your unit city questions, right? And the last part is work done, I'll show you.
Like I said, no starting. It's not as one of the but losses to the house.
Okay, what? Last one. Last one here. This is 2008. 2008, right? That's the best I can do there. Write down your values, please. Write down everything they give you. You're going to need some. What type of motion is this, Adrian? Look at the object. Circular motion, right? Circular motion. So you're going to need some circular motion here to work this out. Take a picture, write it down now.
You can ask your question. I don't know you.
All right, let's start looking it out. So, what they gave us here, Dante?
You get chance to do it.
Now we just write down what they gave us. They gave us the mass 0.5 kilograms. They gave us the original length of the wire. They gave us the diameter of the wire. They gave us Young's modulus as well. And they told you it's moving in a vertical circle. So we had to remember somewhat. Some circular motion, right? So I'll give you a little help because I see they give you some speed later on, I think. Centripetal force is this formula, right? Right, so I just given it back in case you forgot. They also gave us the velocity and they gave us the breaking stress. 7.2 by 10 to the 8 pascals, right? So they gave us all of that. Part 1. Part 1, draw back the diagram with all the forces active.
Yeah,
What are all the forces acting here, Dante?
yeah.
Weight, nice. Sorry? Weight and tension. Okay, nice. And remember that centripetal force is what? You remember what centripetal force here? It's on Nathan looking at something. Nathan, what is centripetal force? Alone? So tension minus weight, right? Tension minus weight is centripetal force. Part 2. At the lowest point, calculate tension. So you have to figure out now how we're going to get tension. And then the one stress. How we getting tension there earlier? Anybody? Emma? Any ideas how to get tension? Nice. So part A. Tension is equal to centripetal force plus weight. Use gravity at 10 if you want, right? In fact, no, maybe 9.8. Use 9.8. Use gravity at 9.8. Adam, you got here for just now. So tension is what? Centripetal force that's 0.5 by 38 squared. What's your use of R? What's the rate of the whole circle? Huh? No. The radius of the part. Remember the length of the string is a meter. So the entire radius is 1. This radius, this diameter here is wire. This R here is the radius of the whole circle. Right? So it's 0.5 by 38 squared root. Plus the weight by 9.8. How much is that potential? How much are they at? 700 and
22,005.
Yes, 722.
7,000.
Alright, that's another look at 722.
Yeah.
Yes. Next part.
You gotta add the,
Oh.
4.9.
Add 4.9.
Yeah.
How much is that? That's the final answer, right? Everybody get up? Right, how we getting the stress? Mikhail, how we getting the stress? Yeah, Mikhail, how much you getting? How much you getting? Mikhail? How you finding stress? Force over area, right? And what is the force we're using? The force. What will be the force on the wire? Tension, right? So that will be tension.
Yes.
Tension divided by area. Remember, you're focusing on the wire. tension divided by area. Hurry up. Divide tension by cross-sectional area. How we get the area? Right, remember you're using this to get the area, right? Pi r squared, right? So that would be 1 by 10 to the minus 3 squared. Any answers? Turn again through. You guys know? Come on, show it again. 2.31 by 10 to the 8th Pascal, right? Last part, extension and wire. Oh, by the way, so does the wire break? Look at the stress value you have. Does the wire break? Look at this stress value that you have. Will the wire break? No. Right? The breaking stress is 7.2 by 10 to the 8. Your value is 2.3 by 10 to the 8. So the wire will not break. Find the extension and we done. Find the extension. And you only module 100. We do fulfill module 1. How will we module 3 and part of part of 1. Yeah, right. Now say I don't know just one question. Right, last part of it, we'll call that part to be done. We need to get extension. What's the formula we use for extension? Go and pick on it. We had to get all here. Go and pick on it. Turn up. So you find it, you got already.
You're ready to do some.
E done, that's mouth. Now we get an extension. Last part and we done.
That's fine.
Look at what we have here, that's really easy. We just find stress and we have Young's modulus, so. Huh? Alright, but you need strain, right? So you need to find strain. Strain is extension over like that. Right? How do we get strain? We already have Young's modulus, right? Young's modulus by stress multiplied by length. Alright, finish up a homework now. Right, so find the strain using Young's modulus and stress and then find the extension. Which one? No, I use the same thing here. I use the same thing. Or rearrange it. That's not rearrange, just find strain. Strain is equal to stress over Young's modulus. Right? And when you find strain, then find extension. Right? So find your strain first. And then multiply it by 11. All right. If you're to take a little break, we'll start.